Section 7.2 is areas in the plane. And again, this is something you've looked at before. You don't need to write this all out. They're starting with our Riemann sum definition. If we take a region and partition it into vertical strips of equal width of dx, then each rectangle has an area of the top minus the bottom, that's our length, times our width, our dx, delta x. And if we add up the sum of all of these rectangles, we have an approximation of the area. If we take the limit of the sums as delta x approaches 0, then we have an integral. So that's the definition we're going to be using. If f and g are continuous throughout an interval a, b, with f of x being greater than g of x, then the area between the curves from a to b is the integral of f minus g from a to b. So this is our function that we're going to be using as we find the area between two curves. The interval may be given to you. It may be the points of intersection of the two curves. So find the area of the region between y equals cos x and y equals sin x from 0 to x equals pi over 3. So we're going to take the interval from 0 to pi over 3 of cos x minus sin x dx. Taking our antiderivative, we have sin x plus cos x, evaluated from 0 to pi over 3. So that's the sine pi over 3 plus the cos of pi over 3 minus the sine of 0 plus the cos of 0. Sine of 0 is 0, cos of 0 is 1. This is root 3 over 2 plus 1/2 minus 1, which gives us root 3 over 2 minus 1/2. Okay, pretty simple integration, but we're starting with our functions as a region between two graphs. Let's look at a couple more. Find the area of the region enclosed by the parabola and the line. So let's draw a sketch of this one. X squared minus 1 looks like this. It's a parabola that drops down 1. The line x plus 1 looks like this. We need to know where these two functions intersect in order to find our integration. So x squared minus 1 equals x plus 1. Setting them equal to each other, I have x squared minus x minus 2 equals 0. That factors. Find my zeros, and I know that at negative 1 and 2, I have points of intersection. So negative 1 comma 0 is a point on both of these lines, and 2 comma 3 is a point. So I'm going to integrate from negative 1 to 2, and I'm going to integrate the function of the top, x plus 1, minus the bottom, x squared minus 1. So let's rewrite that, negative 1 to 2. I'm going to put it in standard form with the highest power first and watch my negative signs. So negative x squared plus x, and that's a 1 plus 1, so plus 2 dx. Let me go to a new screen. Integral of negative 1 to 2 of negative x squared plus x plus 2 is what I had. Antiderivative, negative 1/3 x cubed plus 1/2 x squared plus 2x. From negative 1 to 2, plugging in 2, negative 1/3 times 2 cubed, which is 8, plus 1/2 times 2 cubed, which is 4, or 2 squared, which is 4, plus 2 times 2. All of that minus negative 1/3 times negative 1 to the third power is positive 1/3. Negative 1 squared is positive 1, so positive 1/2 and minus 2. So I've got negative 8/3 plus, this is 2 plus 4 is 6, minus 1/3 plus 1/2 minus 2. So let's see, I've got negative 8/3 plus 6 minus 1/3, so that's going to give me, well, let's keep going, minus 1/2 plus 2. Negative 9/3 minus 1/2 plus 8. So that's negative 3 minus 1/2 plus 8 is 5 minus 1/2 is 4.5 or 9x. Okay? So this is, you should remember this. Now we're going to look at integrating with respect to y. In other words, if the rectangles are easier to do on their side, we are going to use dy slices, and we're going to do the right function minus the left, but I need the point here. I'm going to be looking at my value in terms of x rather than my function value. So let's take a look. So I'm going to be using the first value, not the function value. So we've got a couple different situations here where we might want to do this with respect to y. Let's try one. So I've got two curves here. And again, I'm going to draw myself a sketch. So I've got x equals y squared minus 1. Y squared is a parabola that opens to the right, passes through negative 1. And the line y equals x plus 1, which goes like this. So this is the region that I want, and I'm going to do it with dy slices. So I need to go from 0 up to 1, because I'm integrating from the bottom up. So it's the integral from 0 to 1. And I need points on this graph that are x's in terms of y. So I need to rewrite my line as x equals y minus 1. And then this one is already written as x in terms of y. So the right-hand curve is my y minus 1, minus my left-hand curve is my y squared minus 1 dy. So everything is in terms of y. I'm reading right to left as opposed to top to bottom. So let's, again, clean up my integral that is underneath, that is inside here. So it's going to be negative y squared plus y. I've got negative 1 plus 1, that's a 0. Antiderivative, negative 1/3 y cubed plus 1/2 y squared from 0 to 1. And I am going to plug in my 1, negative 1/3 plus 1/2 minus that whole thing will be zeros when I plug in 0. So negative 1/3 plus 1/2 is negative, negative 2/6 plus 3/6 is 1/6. Okay, so did I do that right? Oh, that was 2/3. Nope. Okay, looking at the wrong problem. Sorry, guys. So I've got 1/6 as my area underneath the curve. All right, I'm going to give you one more, and I'm going to ask you to try this one on your own. And then when you come to class, we'll look at it together. So be sure you do this. Find the area of the region enclosed by the graphs of y equals the square root of x plus 1 and y equals x minus 1 and the x-axis. There are a couple of ways to do this. I want you to work it through. We'll look at the different methods and see what we can come up with as a group. So that's it.